Several definitions to the embedded system. Several definitions to the embedded system. Okay, these are actually I have taken it from the embedded system primer, David E. Simon. The definition of an embedded system. Okay, so like a combination of a computer hardware and the software, and perhaps additional mechanical or other parts designed to perform a dedicated function. This is one definition. The another definition, any computer system whose end objective is not primarily computational. The another definition, any computer system other than the traditional desktop or laptop system. Lately, the smartphone also falls in the category of general purpose computing device. In some cases, the embedded systems are part of a larger system or product, as is the case of an airbag deployment system or anti-lock braking system in a car. Okay. So generally, the embedded system, a system. So here, why it is called as an embedded system? A software is embedded in the hardware. This is the software is going to control. Software means a set of programs. The program means a set of instructions which are going to control the hardware parts. That's why it is called as an embedded system. Okay. So generally, like when in the olden days, they were just calling it as it is a single function. Okay, it is particularly designed for a specific task. Okay, single function, and it is designed for a specific task. So that is the main intention of, main definition of an embedded system. Now coming to the ubiquity of embedded system, it is spread over. The embedded systems are spread over in all the domains. Like for example, if you take a workspace, in workspace, printers, scanners, network switches. In banks, ATMs, passbook printers. Okay. Then the in hospitals, medical equipment like scanners, MRI scanners, and all. Industrial equipment, automation. In agriculture, drip irrigation equipment, soil quality instruments. Okay, in supermarket, point of sale and as well as scanners, point of sale system and the scanners. In defense, missiles, rockets, satellites, spaceports. In transportation, locomotives, cars. Okay, even in automobile, like if you take a car, almost nowadays the cars which are available, 70% of embedded systems are there in the nowadays cars. Okay, in telecom domain, like mobile broadband equipment, okay, modems, switches, telephone exchanges. Okay, in entertainment, projection systems in cinema halls, 4D seats and all. Okay, so this actually I have taken it from the a course. Okay, I mean NPTEL course. So embedded system applications, small and single microcontroller applications, small toys like a remote control cars and all, home gadgets, etc. Control and automotive systems, ABS and cruise control, etc. Distributed embedded control, networked industrial applications and automotive, networking, network switches, just now whatever we discussed again here, critical systems, that is in nuclear power plants. Okay, even in medical emergency, in medical equipment, in aviation devices, in robotics, warehouse robotics, assembly line robots, computer peripheral applications, portable hard disks, printers, scanners. In signal processing, radar signal processing, security cameras. In communication, mobile phones, like if you take the mobile phones here, like the smartphones which we are using will not come under the embedded systems. Okay, so like if you take a keypad based mobile phone, that is especially for the communication, to establish a communication. Like if you take a keypad phone, actually in keypad phone only we can make a call and we can receive a call. Okay, we can send the messages and as well as receive the messages only. That is the function. Okay, so that comes under the category of the embedded systems, even landline phone modems. Okay, so nowadays set-top box in entertainment, set-top box, music systems, noise cancelling headphones, digital picture frames, these are all comes under the category of embedded systems which we are using at home. Okay, even washing machines, RO, purifier, microwave oven, shaving razors. Okay, so these are all comes under the embedded systems which we are using at home. Okay, like air conditioners. Okay, geysers. Okay, nowadays so smart geysers are also available which can be controlled by using our mobile phone, smartphone. Even air conditioners, mood lamp. Okay, so in the case of the examples, in the case of health domain, like treadmill, blood sugar and pressure measurement, fitness tracker watches, utilities, electricity meters, RFID tags, in transportation, car, scooter, motorcycle, electrical bicycle. These are all the examples which we are using, the examples of embedded system which we are using at home. Some observations here, like embedded system observations here. Embedded system is a very big and fast growing industry. Okay, so the heart of the embedded system is a microcontroller, which is actually playing a major role. We are supposed to program that microcontroller. Okay, the software is running on this core, the microcontroller as they call here, the software is running on this core, which makes the embedded system. Okay. Next, comparing the embedded systems and as well as the general purpose computing systems. The embedded system is also a computing, but it is not primarily only a computation. Okay, embedded systems are dedicated to specific tasks. Embedded systems can be implemented using wide variety of processes, even generic to the custom. So we can go for a general purpose or we can go for a customized processes. Customized means which is specifically designed for that. Okay, embedded systems are cost sensitive. Okay, so we will also discuss the design metrics here, the major design metrics. Okay, embedded systems operate under real-time constraints. Comparing the embedded system and as well as general purpose computing systems, embedded systems are often designed to operate in extreme environmental conditions, usually run out of only RAM, read-only memory, where we are going to store the program. Okay, so that program is going to control all the hardware parts. Okay, embedded systems have resource constraints. Embedded systems are infrequently programmed. Okay, so we are not going to modify the program each and every time. Like it's very less reprogrammed. Okay, once it is stored, generally it is a one-time programmable one. Okay, once it is stored, okay, rarely we are going to reprogram it. Okay, if we have some additional features, even if we add some additional features, the hardware is also supposed to support that. Okay, so then embedded systems have hard reliability and correctness requirement. Then coming to the common design matrix, that is a design matrix. Okay, so here the common design metrics are unit cost, NRE cost. What is a unit cost? The monetary cost of manufacturing each copy of the system, excluding the NRE cost, is a unit cost. NRE cost, that is non-recurring engineering cost, that is a one-time monetary cost of designing the system. Then size, the physical space required by the system, performance, the execution time or throughput of the system, power, the amount of power consumed by the system, flexibility, the ability to change the functionality of the system without incurring heavy NRE cost. Time to prototype, the time needed to build the working version of the system. Time to market, the time required to develop a system to the point that it can be released and sold to the customers. This is actually playing a major role. Okay, time to market is actually playing a major role. Okay, so I will also discuss like for example, if you take around 10 or 15 years back. Okay, so if you take any cinema is going to play in several theaters. Okay, the same movie is going to be run in several theaters. Okay, in some theaters it will be at around 9 o'clock In some another theaters it will be at 9:30, and some another theaters it will start by 10 o'clock. Usually, which one we prefer? Usually, we prefer the 9 o'clock show only, because that is a human curiosity. Like, we want to go and we want to watch first. Okay, so that in the way, in the same way, like time to market plays a major role. Okay, so if we have designed, if there is an idea, it is supposed to come into the market as early as possible to get the more benefits. Otherwise, someone will release their products, okay, and they will get the more benefits. Okay, maintainability, the ability to modify the system after its initial release, correctness, safety, and many more are there. Okay, so the major design metrics, like here, the trade-off, like if you see here, if you look at here, if we try to reduce the size, okay, it is impacting the power consumed by the system and the performance, that is the execution time, and as well as the non-recurring, the cost is also going to be improved. So improving the one, like we want to reduce the size, it may worsen the others. Okay, if we want to reduce the size, it may worsen the others, like power consume power consumption and the execution time, and as well as the NRE cost. Okay, so this actually plays a major. These four are the major design metrics: the size, power, performance, and as well as NRE cost. Plays, are very important design metrics whenever we are designing an embedded system. Coming to the, like, the heart of the embedded system is a processing unit. Okay, so here some basic definitions. What is a computer? Computer majorly consists of CPU, memory, and as well as the I/O parts, input and as well as I/O ports. Okay, CPU generally consists of ALU, control unit, and as well as the registers. So coming to the definition of the microprocessor, CPU on a single chip is a microprocessor. What is a microcomputer? Microprocessor, memory, and as well as the I/O ports on a single silicon IC, in a PCB, printed circuit board, is called as a microcomputer. The microprocessor is CPU on a single chip, microcomputer, microprocessor plus memory, and as well as the ports on a single printed circuit board. Microcontroller, microcomputer on a single silicon IC, and then SOC. Okay, SOC, that means system on chip, microcontroller plus, like, based on the application, whatever we are going to incorporate in that, that is like a programmable analog. Like, generally we are working with the digital. If we want to program the analog also, then that is going to be incorporated in the same IC, okay, in a single silicon IC. Okay, if it is fabricated, okay, then it is called as a system on chip. Okay, system on chip, that is, again I'm continuing that, microcontroller plus programmable analog subsystem on a single substrate. Okay, so here generally we are going for the customized functional units on a single substrate with the microprocessor or microcontroller. Customized functional unit means that is based on the application, whatever we require. For example, if you take a digital camera, the video codec and audio codecs are supposed to be, so that can be connected as a separate, the video codecs and as well as audio codecs, coder and as well as decoder, that can be connected to the microcontroller or the microprocessor, or that can be fabricated inside an IC. Okay, so which gives like a video codec and as well as audio codec. Okay, so this is a 6-box model of the embedded system design. Okay, so here this is an embedded computer block. Okay, so to this is a processing unit here. Okay, to this actually we are going to connect the input. Okay, so like input devices like keyboard, mouses, and so on, scanners, whatever the input devices. Okay, and then this is an output. Okay, so the communication block. So to establish a serial communication and as well as a parallel communication, we need a communication block. Okay, host and storage block, where actually the data is going to be stored, and as well as the power supply block. This is a 6 model for embedded system design. Okay, so implementing the embedded computer. Okay, like we can take that computer, like if you see here, so here I can go for a general purpose processor, or I can go for an application specific instruction set processor, or I can also go for a specialized single purpose processor. Okay, so one by one we will discuss briefly here. Okay, general purpose processor, application specific instruction set processor, and as well as a single purpose processor. Okay, so what is like general purpose processors, even whatever we are using nowadays, like these Intel processors and all, i3, i5, i7, these are all comes under the category of general purpose processors. Okay, it can be used for any application. Okay, application specific instruction set processor like digital signal processors and all, these comes under the microcontrollers, the Arduino microcontroller, 8051 microcontroller. These are all application specific instruction set processors. Okay, the single purpose processor which is specifically designed for that particular task. Okay, so like if we see the internal block diagram of the general purpose processor, okay, general mainly it consists of the memory part. So here the memory again divided as a program memory where the program is going to be stored, and as well as the data memory where actually the data is going to be stored, and as well as the sequencer which is going to take the like program counter which is going to have the next instruction address. Okay, so it is going to give the address to here, so the instruction is going to be fetched, that is given to the decoder. Okay, that is given to the control logic, and it is going to give that to the data path where actually the operations are going to be performed. So here ALU, that is arithmetic logic unit, where actually the operations are going to be performed. Okay, so here these are all the temporary memory, the registers here to store the data whenever it is when it is executing the, whenever it is performing the execution operation, the data is generally stored in these registers. Okay, this is a simple block diagram of the general purpose processor. But if you go to the application specific instruction set processor, instead of the general purpose ALU here, the everything is same, the block diagram is same. Instead of the general purpose ALU here, okay, we will be having a customized ALU. Everything is same, the application specific processor. Okay, instead of the general purpose, okay, here we will be having the application specific. Particularly, for example, if you take the old processors cannot perform the operations on for example, if you take an image processor, okay, the image processor means if you have captured a color image, okay, the color image means the primary colors are red, green, and as well as blue. Okay, red, green, and as well as blue. Okay, so here we have generally we have a representation like for a red color we are going for an 8-bit. Okay, for green color, we are going for the 8-bit representation, and as well as for the blue color, we are going for the 8-bit. Okay, so here we have, whenever we want to perform the operations on that, generally, if you take a general purpose processor, okay, so we are supposed to perform these operations one after the another in a sequence. Okay, but when we come to the customized ALU, we can design in such a way that the same operation can be performed on RGB values at the same time. Okay, and even if you take the multiply and as well as accumulate, for example, if you take some mathematical expression like convolution, like whenever we want to perform convolution operations and all, okay, like something like a summation or integration. Okay, so here it will be having a multiply and as well as accumulate unit, by using which we can perform those operations a little bit faster. Okay, so for that purpose, this is a customized ALU here. This customized ALU, okay, which is designed for that particular application. The next one, a single purpose processor. Okay, so here totally like if you compare the single purpose processor with the general purpose processor, the single purpose processor, general purpose processor, the structure is there, like we are going to program that. Okay, the program is going to be stored. Okay, but a single purpose processor, it is totally an hardware part. Okay, so where actually it has a state machine and as well as the data path like a decoder. Data path consists of decoder, muxes, and as well as an ALU here. Okay, so here it is not involved with any programming. By using a program, we have designed a hardware circuit which can always perform the particular task. This is designed for a particular task. By using this, we cannot perform. For example, if it is designed for video codec and audio codec, only video codec and audio codec it is going to perform. It is not going to perform any other operation. Okay. Next, coming to the software hardware co-design ladder. Okay, like if you want to design a single purpose, like to design an embedded system, we have two approaches. One is a software based approach where actually we are going to use a general purpose processor. Okay, in a hardware based approach where actually we are going to design our own single purpose processor. Okay, so here the software based approach, like in both the cases, the sequence first we are to describe the embedded system functionality. Okay, how to describe the embedded system functionality? We are going to write a program to describe the embedded system functionality. That generally we are calling, that is generally like a sequential program that can be written in C or VHDL, hardware description languages like. Okay, so if we want to implement this, I mean, if we are designing the embedded system by using the software based approach, means by using a general purpose processor, we are going to write a program. Okay, so that we can write it in a C language or C++ language. Okay, that is an high level language that is converted into the mission level language by using the compilers. Okay, so we will take a compilers, and by using the compiler is a software. Again, here it is a software tool which is converting the high level language instructions into the mission level language instructions. Okay, or we can write an assembly language instructions to perform the operation, to perform the task. Okay, so we will write an assembly language instructions. That assembly language instructions or assembly language program is converted into the mission level language program by using an assemblers. Okay, so that is assembler is a software which converts assembly language instructions into the mission level language instructions. Okay, that is stored in the memory, and that general purpose processor which is connected to the memory is going to control the hardware part. Okay, so here this implementation is called as a totally a software based one. Okay, coming to the hardware based design, like if you take an hardware based design, okay, we can write a program in C or C++ or even VHDL language. Okay, so here we have several synthesis tools like a behavioral synthesis tool, register transfer synthesis tool, and as well as a logic synthesis tool. Okay, so what is this behavioral synthesis tool is going to do is, so this behavioral synthesis tool is going to take that sequential program which is described where actually the embedded system functionality is described in C language or VHDL language, and that is converted into the finite state mission with the data path. And that finite state mission with data path is given to the register transfer synthesis tool. Okay, that register transfer synthesis tool is going to convert the finite state mission with the data path into the finite state mission, and as well as the a set of logical expressions. Okay, and then that is given to the logic synthesis tool. The logic synthesis tool is going to convert that into the logic gates, and that is going to be implemented as a very large VLSI IC. Okay, it is totally a hardware part. So here this is totally an hardware part where actually initially we will write a program, but finally it will be like an hardware. Okay, so we will get an IC. Okay, so that can be specifically designed for that. We cannot even modify that. Okay, coming to the flexibility, this is more flexible because whenever we want we can change the functionality here, but here we cannot able to change because once the IC has been fabricated, okay, so it will be always doing the same task, okay, which is described here by using a sequential program. It is going to do. Okay, we cannot change the functionality. Okay, if we want to change the functionality, we are supposed to go, I mean, we are supposed to change the program, and again we are supposed to do all these operations, all this like synthesis, and finally again we are going to get another IC, okay, which can be the which is added with the additional features. Okay, so generally some designers will go in this approach, some designers will choose this approach, but whenever the design metrics will come into the picture like a cost, size, performance, and as well as the power, okay, we need to go, okay, we need to go this we need to choose this hardware based approach. Okay, so this is about the software hardware co-design ladder. Okay, so here's one simple example. Okay, so this is a simple block diagram of 8085 based roulette. I think everyone knows about the roulette. Okay. So this is a simple, and this is a circuit which is actually I have taken it from the, I think in other colleges. So they have done this actually. Okay. So here this is 8085 based roulette wheel game. Here 8085 microprocessor is there, so it is going to generate the random numbers, and that is going to be displayed here. Okay. Then the same thing can be designed by using the microcontroller. Here the Arduino based roulette is here. Okay, so this is Arduino Nano is used here. Okay, even we can also go for a general purpose, single purpose. Okay, so this is an Arduino based one. Okay, we can also go for the a specific a single purpose processor which is specifically designed for this roulette. So this is actually which I want to discuss. Okay, so even some tools are there. Okay, like a Tinkercad, where actually we can work in a virtual mode. Okay.
Yeah.
So, thank you, sir.
Thank you, sir, for your nice presentation. So, participants, if you have any queries, please ask us. Participants, you can raise your doubts. Okay, sir. Thank you, sir.
So thank you, sir.
Thank you, sir. Thank
Thank
you,
you.
all the participants. Okay, with this, we'll close this session. So, thank you, sir. Thank you.
Okay. Thank you very much, sir. Thank you for everyone who involved in this process. Thank you. Thank you very much, sir.
Yes, sir. Yes. Okay. Thank you, sir. Okay. Bye.
Thank you.